Okay, so now let's go do some examples. So in each of these situations, which distribution do you use, the Z or the T? If there are 500 million people on Facebook, how many people have fewer friends than Diana, who has 490 friends? Assume that the number of friends on Facebook is normally distributed. Aha! And here, they give you the sigma. So we know that you could use the Z distribution here. Here, the researchers want to compare a given sample of Facebook users' average number of friends, 25, to the entire population. What proportion of sample means will be equal or greater than the mean of this group? Right? N equals 25, but the mean is 580. So they have an average of 580 friends. Well, here, I definitely wouldn't use, I wouldn't necessarily use Z, but then I also don't have the standard deviation. So maybe this is connected to this previous problem. If so, if I assume that they come from, oh, yes, I see, the whole population, and they give us the information for the whole population here, if, sigma equals 100, then I'll use Z, right? So this one, I probably left out some information. All right. So what about this last one? Researchers want to know the 95% confidence interval for tagged photos, given that a sample of 32 people have an average of 185 tagged photos and a standard deviation of 112. Here, it's very clear. Since I know S, right? I know S, but I don't know the sigma for tagged photos, right? I only know the sigma for friends, but not for tagged photos. In this case, what I would do is use the T distribution, because I'll probably have to estimate the population standard deviation from the sample standard deviation. Okay, so example 2. So what we get is that problem, and we just have to solve it. So if there are 500 million people on Facebook, how many people have fewer friends than Diana? Well, here, it's good to know that we don't need a sampling distribution of the mean. We don't need the SDOM. In fact, we're just using the population and Diana, right? A sample of 1. So we could draw the population, and it tells us that the population is normally distributed. So number of friends, right? It's normally distributed. Yay, it gave it to us, right? And so the mu equals 600. And the standard deviation, here's 1, here's 2, here's 3, okay, is 100. So this little space is 100. So this would be 700, right? Okay. So Diana has 490 friends. So that would be, so here would be 500. So something like this, right? And it's asking, how many people have fewer friends than Diana? So how many have that, right? Now, it's tricky because this will give us the proportion, but it won't give us how many people, right? What we'll have to do is multiply that proportion to the 500 million, right? So this is all 500 million, right? That's 100% is 500 million, right? And we'll need to know some proportion of them that have friends fewer than Diana, fewer than 490, right? And so we'll have to figure that out. And so we'll have to multiply 500 million by that, by the percentage. Okay, so let's get cracking. So we could figure out the z-score right here, the z-score for Diana, right? And that would be 490 minus 600 divided by, do we need standard error? No, I want to find it just in terms of standard deviation, right? So standard deviation, which is 100, right? Because I would only need to do standard error if I was using the SDOM, but I'm using the population standard deviation. That's why it's often helpful to draw this. Okay, so here we have about 110, negative 110 divided by, divided by 100, right? So negative 1.1. Okay, so I have a z-score of negative 1.1. So it's 0, negative 1, negative 1.1, right? And I want to know everybody who has the proportion of people who have friends less than Diana. Now you could look this up on the back of your book. So I would just look up, the z-score of negative 1.1, see what's there. Or you could put it into Excel. Norms dist negative 1.1. And I should get about 1.1357. So that would be 0.1357, right? So about 13.5% of the population have fewer friends than Diana, right? So what I want to do is only get 13% of this entire population. So that would be 500 million, right? I don't really need to put all those zeros. Multiplied by 0.1357. And you could do this on a calculator. So that times 500 million, right? So I get 67.83 million. 67.83 million. So don't forget to put that million part, because it's not that you have only 67 people who have fewer friends than Diana, right? So that would be our answer right there. Okay, so the researchers want to compare a given sample of Facebook users' average number of friends, 25, a sample of 25, to the whole population. What proportion of sample means will be equal or greater than, I think, equal to or greater than the mean of this group? Well, here I'm going to assume, because there's no other way in order to do this problem, I'm going to assume that we could use the information from example 2, right? Because we're talking about the same thing, the number of friends, right? And so we actually know the population. So the population is approximately normally distributed. It's approximately normal with a mu of 600 and a standard deviation of 100, right? So mu equals 600, standard deviation equals 100. Now from this, I need to generate an SDOM, because now we're talking about samples of people, not just one person at a time. So because of that, I need to generate an SDOM for n equals 25. So the nice thing is, just pretend it's lined up underneath that. The nice thing is we already know the mu sub x bar. Mu sub x bar equals mu, so that's 600. But we actually also know the standard error, because standard error is standard deviation divided by the square root of n. And in this case, it's 100 divided by square root of 25, which is 20, right? And so one standard error away here is 20, right? So this would be 580, this would be 560, so on and so forth. And it asks, what proportion of sample means will be equal to or greater than the mean of this group? Equal to or greater than means all of this. And they're just asking for proportions, so we don't have to do anything to it once we get the answer. Well, it might be nice if we could actually get the z-score for this SDOM, right? And so here, instead of just putting 580, I'd want to find the z-score here. So here's raw friends, but I want to know it in terms of z-score. Well, it's actually really easy because it's a z-score of -1, right? And we could actually just use the empirical rule to find this out, because we know that at the mean, at the expected value, we know that this is 50% and this is 30, 4%-ish, right? And so if we add that together, the proportion of sample means greater than or equal to the mean of this group, right? That equals the proportion where the z-score is greater than or equal to -1, and that is 0.84, right? So 84%. Final example. Researchers want to know the 95% confidence interval for tagged photos, given that, that a sample of 32 people have an average of 185 tagged photos and a standard deviation of 112. Interpret what this CI means. Okay, so here we don't know anything about the population, but we do know X bar, which is 185, and we do know the standard deviation of the sample, small s, which is 112. We also know n, right? We have 32, right? And remember, when we talk about confidence interval, we want to go from the sample to figure out where might the population mean be, right? So what we do is we assume that we're going to draw a pretend SDOM here, right? And we assume that the X bar is going to equal the expected value of this SDOM. So that's 185, right? And from there, we could actually estimate the standard error by using S, right? So here in this, mu sub X bar equals 185. This is assumed. And not sigma, but S sub X bar is S divided by square root of n. And in this case, it would be 112 divided by square root of 32. And if you pull up a calculator, you could just calculate that out. 112 divided by the square root of 32 and get 19.8. So 19.8, right? So we know how far the jumps are, right? And because we used S, we can't just find the z-score. We'll have to find t-score, right? And we'll have to use t-score in order to create a 95% confidence interval. Now, although we don't know, because I don't know what a t-distribution for a degrees of freedom of 32 minus 1, 30. I don't know what a degrees of freedom of 31 t-distribution looks like. I really don't, right? So we'll have to figure that out. What we eventually want is this to be 0.025, 0.025. So these are together a combined two-tailed probability of 5%, right? And so we'll have to use t inverse because we already know the probability. We want to go backwards to find the t. So t inverse, and we put in our two-tailed probability, 0.05, and we put in our degrees of freedom, which in this case is 31. And we ask, what's the t? And it says it's 2.04. So the t right here, right, at these borders, is 2.04. And because it's symmetrical, we also know that this one is negative 2.04, right? And so in order to find the confidence intervals, we're really looking for these raw values right here, right? And in order to get that, we add the middle point and add 2.04 standard errors to get out here. And we subtract out 2.04 standard errors to get out here, right? So the confidence interval will be X bar plus or minus the t-score, how many jumps, multiplied by how big these jumps actually are. And that's this score right here, multiplied by S sub x bar, right? And if we actually put in our numbers, that's going to be 185 plus or minus 2.04 times 19.8. So if you just pull up a calculator, we could get 185. Make sure to put that equal sign, 185. Even I forget sometimes. Excuse me. Plus 2.04 times 19.8. And remember, Excel knows order of operations. It'll do the multiplication part before it does the addition part. And so the high limit, the upper limit, will be 225.39. And the lower limit will be 144.61. I'll just round it to the nearest tenth. And so this would be 225.4, and this would be 144.6. Sorry, it's a little small. All right, so now we need to interpret what this CI means. This means that there is a 95% chance that the population mean will fall in between 144.6 and 225.4. So